Functional dependencies constitute a set of rules which are crucial for verifying data quality. In this talk, we will discuss an approach that incrementally cleans functional dependency violations as the user explores and analyzes data. To analyze real-world data and extract actionable insights, data scientists need to perform a set of pre-processing steps. As we can see on this pie chart, 60% of the data scientist's time is attributed to cleaning and organizing data. The reason for this is twofold. First of all, data cleaning is expensive because detecting errors requires multiple pairwise comparisons between the tuples of the dataset in order to identify conflicts. And what is more, in order to repair the detected errors, we might need to solve constraint satisfaction problems in order to find the values that satisfy all the constraints. Even that is sometimes not sufficient because we might need human effort in order to either annotate the repairs or even worse, to manually fix some of the errors. Another dimension of the problem is that the users identify rules at data exploration time. For example, data scientists in Nestlé often want to analyze coffee products in their database, and as the database is dirty, they might stumble upon several errors like the one shown on the screen, where the Robusta bean appears both as a coffee and as a chocolate product. Therefore, a user might want to go back and define a functional dependency that states that the type of bean determines the product category and then detect violations of this rule. Therefore, we observe that the process of data cleaning is expensive and depends on the analysis that users perform. To perform analysis over dirty data, a traditional approach would just take the dirty database, apply all the cleaning tasks offline, and then execute the queries over the clean version of the database. However, to address the aforementioned issues of offline cleaning, our aim is to allow queries directly over the dirty database in a way that the query results that we get are equivalent to the ones that we would get if we create directly the clean database. The main benefit of this is that we can clean only the part of the dataset that is interesting for the user. For example, if our analysis involves analyzing the clients that live in Los Angeles, and these clients participate in a violation with the clients that live in San Francisco because they have the same zip code but different city name. So in this case, we can directly provide correct answer to the queries that involve the clients in Los Angeles without accessing the clients that live in New York. In addition, as we apply cleaning at data exploration time and we have partial knowledge of the rules, we provide probabilistic candidate fixes. And we do this because automatically inferring the correct value without having a knowledge of all the rules that exist might be inaccurate because because in order to fix a dirty value, we need to have knowledge of all the rules that it violates. Therefore, to address this problem, we use attribute level uncertainty, where each attribute that participates in a rule might get multiple candidate values. Then the probabilities of each candidate value are frequency-based, and they are driven by the conditional probabilities that are given by the functional dependencies. Therefore, for example, here, the zip value 9001 is mapped with two different city values, Los Angeles and San Francisco, each with a 50% probability. Therefore, using this approach, we can clean only the useful subset of the dataset using the probabilistic fixes. So to integrate cleaning with querying, we need to introduce cleaning operators inside the query plan. And as the cleaning operators depend on the underlying query operator, we distinguish between select and join cleaning operators. Therefore, for select project queries, we use the clean select operator, which takes as input the dirty select result and outputs the correct result. And the steps of the clean select operator are that it first relaxes the result by bringing correlated tuples from the dataset. And these correlated tuples involve tuples that are candidates to qualify the conditions of the query, or they are tuples that are useful in order to clean the result of the query. And then after enhancing the result with the extra tuples, the clean select operator cleans the result and then updates the dataset with the probabilistic fixes. And therefore, based on this, we gradually transform the dataset into a probabilistic dataset. So let us now see how the clean select operator works through an example. Let's suppose that we need the information about the customers that live in Los Angeles. So the query result would first bring the first and the third tuple, and then using transitive closure, we start bringing correlated tuples. So first we bring the second tuple, since it also has the zip code 9001. Then similarly, we bring the fourth tuple, since it has the city value San Francisco. And then we can stop the transitive closure because we already have the values that are candidates to take as city Los Angeles. And these are the ones that have a zip code 9001. And we also have the tuples that are required in order to fix the domain of the zip code. Therefore, based on this information, we can compute the candidate values and their probabilities using the conditional probabilities, similarly to what we mentioned already. And therefore, the first tuple has two candidate values for the city. And we also observe that the second tuple has two candidate words, two candidate pairs of values, and these are in the case where we either fix the zip code in the conditional probabilities or the San Francisco, or the city value, which is San Francisco. Therefore, using this approach, by relaxing the results, we can partially provide correct query answers without accessing the whole dataset. So now, in the case of join queries, we introduce the clean join operator inside the query plan similarly. However, in this case, where we have join queries, an error that appears in each of the involved tables in the join might affect the join result. For example, if we have a join query between relation R and S, and relation R involves violations of the functional dependency in which between the zip code and the city. So a dirty result of the join of the two tables would involve the pairs of these tuples shown in red boxes. However, in order to fix the errors, we relax the result of relation R by bringing also the first tuple, since it has the city value Lausanne, and therefore the zip code of the first tuple would have two candidate values, 1007 and 1000, and therefore it will pair with the first tuple of relation S. Therefore, we need to update the join result after relaxing the result. And to do this, we do it incrementally by taking only the difference in order to avoid recomputing the join from scratch. So the corresponding query plan is shown on the right-hand side of the screen, where we first perform the join between the two relations, then use the clean join operator, and then incrementally update the join result. So to evaluate our system, we use three datasets, one synthetic and two real-world datasets. For the synthetic dataset, we use the star schema benchmark, and specifically the line order and the supplier datasets. And we do this in order to stress the performance of our system. And then we use the Nestlé dataset and the dataset with air quality measurements in order to simulate real-world exploratory scenarios. So our workload consists of select project join queries, and combinations of them. And since our implementation, we have built our system over Spark, we evaluate it over a 7-node cluster. So in this experiment, we measure the response time of our system first given a set of select project queries, and specifically we use a workload with 50 range select project queries, which are non-overlapping. They have the same selectivity, and in the end, they access the whole data set. So on the x-axis of this graph, we have the percentage of violations in the case of line order in the line order data set, and on the y-axis we have the response time, and we compare our approach, which we call DAISY, which incrementally cleans the data set through the queries, with the offline approach, which first cleans the whole data set, and this time is shown on the black bar, and then performs the queries, which is on the gray bar, which is negligible in all cases. So we observe that in all cases, DAISY outperforms the offline cleaning approach because it checks only the correlated tuples with the dirty tuples and avoids having to traverse the whole dataset multiple times for each error. So we also, in this case, evaluate the case of a mixed workload, which involves select project and select project join queries. Again, we have the same setup where we have 50 range queries with the same selectivity, and they access the whole dataset. Therefore, again, we have a worst case scenario, and we observe that again, DAISY outperforms the offline approach, and due to the correlated tuples that it maintains. And in addition, we observe that despite the fact that we have to recompute the join, since we do it incrementally, the response time remains unaffected and is still low. So in this experiment, we measure the response time of 2 real-world exploratory scenarios. First, we evaluate the response time of our running example, where we execute a set of queries over the Nestlé database to look for coffee products. And we also evaluate an exploratory analysis scenario from Kaggle, which analyzes carbon monoxide measurements over the states and territories in the US. For the case of Nestlé, we use 2 versions of the dataset, a smaller and a larger one. And in the smaller one, we observe that the difference in the response time is mainly due to the fact that the query workload accesses 40% of the dataset. However, when we, in the larger version of the dataset, the difference is more significant, and the reason is that the product category has a very low selectivity, and therefore its product category appears with multiple different materials, and therefore in order to fix the domain of the dirty materials, an offline approach would traverse the dataset multiple times, which we avoid by maintaining the correlated tuples. So the case for a quality dataset is even worse because the dataset is larger, and therefore the offline cleaning approach was non-responsive after a timeout of 1 day. So to summarize, we presented an approach that gradually cleans the dataset through exploratory analysis queries. And we do this by integrating cleaning operators inside the query plan in order to provide correct query answers. And our experimental evaluation showed that our approach DAISY can scale better than offline cleaning approaches. Thank you.